Okay, so again, yeah, if you want to post a question, and then you go to this slido.com, and then if you enter KUDL, and then it says sorry, there is no such event active right now, but you should be able to see this past event. Okay, so yeah, so basically you click the event shown as this past event, and then click it, and then joining it, and then you should be able to just use the same board. Okay, so I think I explained the effect of the bias, which is really our kind of bias that we have. For example, if we believe that, given no information, we are not given any information yet, and then we have our own kind of prejudice or some kind of bias in our thoughts, in a way that so we will more likely to see dogs than sheep in our life, because it's much more often the case to see dog or cat than seeing a sheep in our life usually, right? So that is kind of our bias. So given no information, we give relatively more probability to see a particular class, and that is corresponding to our bias, and that is reflected as this constant term. And and why this bias term is working as our really perceptual bias is we assume that given no information, our given a linear layer like this, and then we assume typically this W and X are all zero-centered, or the mean value of our parameter and also our feature value of this X, whether it's a vector or a scalar, and they are having the zero mean. So if we multiply them together, and then those product will also be the zero mean, right? And so this B, so suppose this one is corresponding to the dog, and W1, B1, and this is Y2 is W2, X plus B2, and this is corresponding to sheep. And then, if those two values are roughly the same as 0, and then B1 and B2 will work as the something which is an input to our softmax layer, and that was our quiz. One of the quiz problem. What is this? What is this called? Which is this linear combination output that will be the input to the softmax layer. So what are they called? What are they called? 로지. 이거 비디오 봤어요? 네, 오늘 아침에 봤을 때는 그렇게 많이 조회수가 안 높아갖고 좀. Okay, so it's called logit, right? And so if this value was this value was 3 and this value was 1, and then how do we compute the softmax? To e to the power of 3 and e to the power of 3, and then e to the power of 3, and so this will be the probability of this guy, and then suppose, so this guy is into 0, and then this bias value is actually 3 and 1, and in this case we are imposing that this guy has the larger probability values, right, given no information. I mean, a priori, or given no information, we assume that this guy has the more probability than this guy, and what's the ratio of that probability? It is like this one, right? Because this guy between these two probability, so this guy times e to the power of 2 will produce this probability, right? And so that is the bias, or our kind of prejudice that we have given no information. Okay, any questions about it? Okay, so and also we discussed about the hinge loss, and why the margin of the value of 1 is just used as a fixed value, right? Because we can just simply scale our W and B into larger or smaller value, and then the margin will not have any effect at all, right? So this class imbalance, the effect of this class imbalance is actually related to this bias. So given, I mean, in what situation will this B1 is larger value than this B2, right? So that, the main cause of having larger bias value is because we see more number of data items corresponding to this class, for example, like dog class, than the number of data items of sheep in our training data. So suppose our training data has maybe 1,000 dog images, but only 200 sheep images. In that case, our bias will be will be assigned as a larger value for the majority classes. Okay, so it's not always the case, and this ratio, or like this ratio, is not reflecting the exact ratio of these training data items between different classes, but roughly you can think of them as the same thing. Okay.
Explain the question in English for me before you go through.
Okay.
Sorry.
Yeah, okay. So this question is, what's the impact of class imbalance to the deep learning? Okay. So class imbalancedness means, among the classes that we have to classify, so the ratio of the training data item are quite different across different classes. And so, so that way, if we observe that we have much more training data items for this particular class than the other classes, and then such an effect will be reflected typically into the bias value. Any other questions? So so usually this prior knowledge, I mean, if you studied the Bayesian statistics or Bayes rule or something like that, like prior likelihood and posterior. Have you heard about it? Prior likelihood and posterior. And usually this prior thing, I mean the prior probability is determined or predefined in advance, right? So, for example, our parameter will follow the Gaussian distribution that has a zero mean and the univariance, but actually our optimal parameter determined by the maximum likelihood estimator is actually maybe 5. For example, so it may make sense only if you are familiar with this maximum likelihood estimation or things like that. So something like this. So suppose we observed some statistics of observations like a person's height as maybe 170, 165, 175, maybe 180, and then in this case we can easily compute the sample mean of them, right? And then the sample mean will be right? So 172.5, right? So this is typically called the sample mean, right? And also if you studied this kind of maximum likelihood estimation, and then you can derive that sample mean is actually the optimal estimator for our parameter, which is the true mean of our underlying distribution of that person's height, right? But when incorporating the prior in the context of Bayesian statistics, and then we impose some prior knowledge or prior belief or our kind of prejudice that, okay, the person's height, given no data at all, so before actually observing these data, we have our prior beliefs that, okay, so person's height will have the true mean value as 170. Okay, and also the standard deviation of 5 centimeter. Okay, and also we also have the prior knowledge or prior belief that, okay, this person's height will follow the Gaussian distribution. Okay, so in that case, the Gaussian distribution will only require or need those two parameters of mean and the standard deviation, right? So that way we have our own prior belief, right? And then this prior belief and also purely driven by our data, it is saying that our optimal mean value should be 172.5, right? So usually this guy and this guy is actually weighted averaged as the posterior estimation or Bayesian estimation. Okay, so in this case this is our prior knowledge. I mean, if it doesn't make sense, and then it should be okay. But here the point is that in this case, this kind of belief or information is predefined in advance before looking at our data, right? But this, those data can also be determined, or this prior belief can also be determined by looking at just the data in a simpler manner. Okay, so in this case, what is our prior belief or the prior knowledge related to that bias? It is related to the belief that we have much more probability of observing this dog class than the sheep class, right? So that is our prior knowledge, and that ratio is 5. Okay, so that where did this prior knowledge come from? That was also from our data, right? So such an information of having 5 times more probability for the dog, then the cat, dog, then the sheep. Yeah, that was coming also from those simple distribution of our training data, right? So in that case, our prior knowledge is also determined by our data by taking a simple approach, right? But the actual way of determining this bias value of B1 and B2 is based on the backpropagation, right, through the gradient descent, right? So those two values are not, just simply determined as those two values having this exact same ratio, right? So we have our own way to determine the optimal parameter value of B1 and B2, right? So that way, you can view this kind of, our main kind of way of determining B1 and B2 as some kind of a likelihood value, but also we have this kind of prior knowledge, but this prior knowledge is also determined by our data, okay, in a simpler manner, okay. So simply answering this question, prior knowledge, I have to explain this question. The question is whether the prior knowledge is also data dependent. The answer is yes, right? But it's not always the case. We can impose the prior knowledge as the fixed knowledge. So any questions? Okay, then K divergence is it a metric or not? If you watch the lecture video, it is not, right? So K divergence is not a metric, and which requirement does it not satisfy? Symmetry, symmetry. So right? Because this, why is it not equal? Simply because the definition is using P and Q in a different manner, right? So this was our definition of this K divergence, right? And so if P and Q are switched, and then this definition will become different. And so it is not symmetric. And also, although I haven't proved it, but this K divergence does not satisfy the triangle inequality. Okay. So what is the triangle inequality? We introduce or we consider third distribution as R, for example. Okay, and then this K divergence should be something like this, right? So so this is not always true in the case of K divergence, and so that way it is not a metric. Any questions? Okay. And let me address this first question. So the question is about stacking linear layers, and then why is it equivalent to just using a single layer? Okay. Okay, so So let's consider this two layers which are composed of just linear layers with no nonlinear layers in the middle. And so in this case, I'm gonna just assign some particular parameter value. So in this case, what is our function? Yeah, C is f of y. Okay, let's say it's g of y. So this layer is called g, and this layer is called f. And then, yeah, it is like g dot f. Okay, and in this case, g of f of an x. I'm just writing just a simple composite function. Okay, so in this case, what is fx? So y equals fx, because this f output of this layer called f is y, right? And so 2x plus 3, and z is f of y, and it is 4y plus 5, right? And so this c is 4y plus 5 and 4, and yeah, if we just plug this in, then 8x plus 17, right? So it's now represented as one single layer. I mean, one single linear layer, right? So stacking these two linear layers, yeah, has no meaning. I mean, it doesn't have any effect. In that case, you can just use, I mean, you can replace these two linear layers into one, okay? But this is not always true. This is not always true, okay? And actually, we sometimes use, or yeah, some famous methods in the context of natural language processing, which is called the word embedding, like word2vec or glove. Yeah, you may want to use it at your project. So, yeah, if you are interested in this, yeah, natural language processing and this kind of domains, word2vec or glove. Yeah, it's small l. Yeah, but anyways, yeah, those two are two different representative methods for word embedding. Okay, so you will have a chance to study that, because I'll ask you to study that in more detail. But anyways, this word2vec is a method that uses just two linear layers. Okay. And yeah, as I mentioned in this particular example, it doesn't make sense, at least in this case, right? But when does the two cascaded linear layers has the effect or different from one linear layer? So it is like this. So suppose we start from x and 1, and then we obtained y, right? And then, so back to this example. So we have input and hidden and output layer. And what is the number of nodes in the input layer? We have just a 1, right? Because we don't usually count this bias as a input dimension, right? So we have one node in the input, hidden and output node, right? But what if we have a different number of nodes? Okay, so in this case, let me just add another node in the output layer. Okay, and then let's suppose we just cascaded two linear layers, and then it's 2 and 3. Okay. Okay, and then so we have one here, and then the fully connected layer is defining like this, right? So Z1 has its own function of G1 of Y, right? And Z2 has its own function of G2. Okay, so in this case, let me just assign some number 4, 5, and 6, and 7. Okay, so in this case, Z1 is 4y plus 5 and 6y plus 7, right? And so what was y? Y is 2x plus 3, right? And then let me just rewrite it. It's just the same thing as this guy, right? And also, what about this? And then it's like this, right? Okay, so in this case, it is still the same as, let's see. Okay, so I have to modify this example in a slightly more complicated one, but the point that I'm trying to make is as follows. So we have a Z1 and Z2 as its own linear representation or linear combination, right? And then we want to be able to represent each of Z1 and Z2 as a linear combination of X, right? And then in that case, let's just consider single layer case, Z1 and Z2, right? And then in this case, it's X, and here we will have 1, right? And then we have a freedom of assigning any linear combinations to make Z1 and Z2, right? But in this case, is it always possible to have just one node in the middle? Okay. So in this case, it is actually possible in this particular case, but if we just add another layer of x1 and x2, okay, x1 and x2, and then suppose this guy was 2 and maybe 3 and 4, right? And then this y will always have like x1 times 2 plus 3 times x1 and 4, right? And then it is multiplied with 4 and plus 5, right? So that will be this Z1, right? So in this case, let's look at the ratio between x1 and x2. So in this case, it's a little bit messy, but this is Z1, and Z2 is 6 times 2x1, 3x2, 4 plus 7, right? So it's just a slightly more complicated case where I added another input node, right? So in this case, so it's 8x1 and 12x2, right? So in this case, 12x1 and 18x2, right? And some value, right? And in this case, for our Z1 and Z2, the ratio between x1 and x2 and their coefficient will always have the fixed ratio that was determined at the first layer, right? This guy, 2 and 3, right? So in this case, if we just cascaded these 2 linear layers, and then it will no longer be able to represent Z1 and Z2 as just an independent linear combination representation of an x1 and x2. So in other words, Z1 should always have x1 and x2 as the ratio of 2 to 3, and also z2 will also have the same ratio, right? So yeah, you cannot break those ratio between x1 and x2 because that ratio was determined in the first layer, right? So in this case, actually, even though we have two linear layers, I mean, which one is more powerful one? Like x1, x2, and 1. So this will be, yeah, one linear layer representation of having the same input and output, right? Two input of an x1 and x2, and two output of an y1 and y2, right? So this is just one layer version, one linear layer version, and this one is two linear layer version. I mean the cascaded one. So which one is a more powerful model? So following this storyline, I think in this case of having two linear layers where we have only one single node in the intermediate layer, that will be more restricted model, right? So you cannot really, yeah, have those different ratios between x1 and x2 for z1 and z2, right? So does it make sense? So it's much more constrained model. 이해가요? 이해 안 가는 사람? 다 가요? 다 가죠? Okay, so so that way, this kind of approach is called, sometimes called the bottleneck structure. Okay, bottleneck structure, because we have more number of an input and more number of an output node compared to the number of nodes in the intermediate layer. Okay, so it's like if we generalize this form, and then we have really long vector as an input and long vector as an output, and like this. So in this case, even if we cascade two linear layers, and then yeah, it will be much restricted representation when having just a single linear layers. Okay, and also we can also understand or observe their number of parameters. Okay, suppose we have a 10 nodes and maybe 3 nodes in the middle, and then what will be the number of parameters that is required to construct this neural net? So what will be the number here? So we always have to consider additional bias node, right, through our bias trick. And so in this linear transformation matrix, we'll have 3 times 11, right? So 33 number of parameters. And also similarly, it's additional bias node, and so 4 times 10, so 40. So in total, 73 nodes, right? Okay, and then let's just consider one linear case of having 10 and 10 input and output nodes. And in this case, we have a bias over here, or this additional kind of dummy node. And then our number of parameters will be 110, right? Which is larger than 73, right? So even though this guy is just a single layer and this guy is the 2-layer neural net, I mean more number of layers, but the number of parameters may actually be smaller than the single layer one, right? So that way we can kind of intuitively understand that model on the right is more powerful or more can represent more flexible characteristics than the left one. And also, if you are familiar with the linear algebra, and then this guy is related to the low rank matrix factorization. Okay. Yeah, but I'll skip that part, and I think you will have a chance to look at this matrix factorization in more detail when studying the word embeddings. Any questions? Okay, then, once we add this nonlinear layer in the middle, such as what is this called? Max of our output and 0. So that is called the ReLU. So ReLU is the function like this. Okay. So if we have, this y node had maybe value of 4, and then this nonlinear layer called ReLU will just give the same value if it is positive value, and then if it was negative value, and then it will change it into 0. Okay. Okay, so I believe I addressed this question on top. Any questions? Okay, then. So carrier divergence is not the same as cross entropy, right? So I already explained it in the lecture video. I recorded in some other countries. Yeah, it was a little difficult because the internet was quite slow, and also carrier divergence is not a metric, and softmax loss is the same as the cross entropy loss. They are the same thing. Do you want me to explain a little bit more details? If you want, please raise hand. Okay, and then entropy is 2 to the power of perplexity. It is actually the opposite one. Perplexity is 2 to the power of entropy, right? So, and I think I gave the some intuitions about how you understand the perplexity. But perplexity is what is the meaning of perplex? Perplex. 한글로 뭐죠? perplex가? 약간 GR이라고 토플에도 나오나 그런 perplex 동의어 한 10개쯤 외우는데. 네, perplex는 뭔가 당황하게 하다 뭐 이런 거요. 동의어 하나만 해보죠. 동의어 뭐였죠? 네? Embarrass. Embarrass. 많아요. 네. Okay, so so the perplexity is the degree of being perplexed. Okay, so it's about the confidence or uncertainty of the outcome. Okay, so suppose you played some poker with your friend, and then suppose you are quite certain that what the opponent has has in terms of its a particular card value, face value, or something like that. Okay, so 이거 어렵네. 도박을 영어로 하려니. Okay, but So perplexity is something like this. So suppose you have, we roll a dice, and then dice has always producing the fixed value of maybe 2. Okay, even though it has 6 different values, but from your empirical experiences, and then you always observed that this dice is producing the fixed value of 2. Okay, so in this case, what would be the perplexity? I mean, the degree of being perplexed by watching the unexpected values. So in this case, there is no perplexity, right? Or there is no uncertainty, right? Okay. And then what about this case of our dice? Yeah, even though it has 6 different values, but our empirical experiences says that our dice is producing equally either 2 or 3. So in this case, we can expect our outcome to be just between 2 of these values, right? So in this case, we will be kind of perplexed, I mean twice kind of more than the first case of expecting just a single value, right? Okay, so the number of possible cases that we can expect can be just understood as a perplexity. So in this case, the perplexity will be 2, and what about this case? It is if we are certain that we will observe this outcome will be just a fixed value of 2, and then it will have the perplexity of 1. So you can roughly or intuitively think of it as the number of possible outcomes that you can expect. Okay. Okay. So in this case, I mentioned that we have there is 0 uncertainty, right? We are 100% certain or sure that our outcome will always be this 2, right? And so in this case, what will be the entropy or uncertainty? In this case, entropy will be 0, right? Entropy will be 0. And that entropy, 2 to the power of the entropy is actually the perplexity, right? So it means that, the possible outcome that we can expect will be just only 1, okay? So that is the same situation that, we have 0 uncertainty. Okay, so this perplexity is quite often used for the evaluation measure. Okay, so suppose we perform the 10 different classes and multi-class classification among 8 different classes. Okay, so in this case, what will be the random guess and their perplexity? I mean, what will be the perplexity corresponding to the just pure random guess? I mean, random guess will be just picking up, one among the 8 different values equally. So in this case, perplexity will be just an 8. Okay, but somehow you trained your classifier very well. Okay, and then given the input feature value, input feature vector, you are always you are 100% certain that given this particular input feature vector, the correct classifier is this particular one. Okay, so in that case, given our input feature vector or input information, the situation is something like this. Even though we have 6 different face values of our dice, but in this particular situation, we are certain that outcome will be 2, right, with 100%. Okay, so in that case, from the classification perspective, our classification accuracy is 100%. Okay, so in this case, what will be the perplexity? Perplexity will be 1. Okay, so if you read some papers and then see the perplexity being 1, and it means like perfect classification. But what about the perplexity being 2 or maybe 1.5? Okay, in the which is somewhere in the middle between 1 and 2. So in the case of 2, and in that case, given the input feature vector, and then your classifier is actually equivalent to random guess between only 2 of them, only 2 of the possible classes. Okay, so that is yeah, that is the intuitive understanding about the accuracy measure of your trained classifier. Okay. Any questions so far? Okay, the answer for this question is logit. Okay, so this was covered, right, in the class, I mean the lecture video, and also in the CS231 and original video lectures. So so this is our softmax loss, right? And then if we just perform the random guessing on this case, and then picking up randomly among the 4 different classes, and then I mean the picking up the ground truth class will be just 0.05, right? So that way it's like this, and so the loss is 2. And then what will be the perplexity? So this is the perplexity is 2 to the power of 2, so the perplexity will be 4. Okay, so as I mentioned, if the perplexity is 4, and then our classifier is like doing the equally picking up among 4 different classes. Okay, so that way the perplexity is related to this cross entropy or K divergence and things like that. Okay. Any questions? 네.
퍼플렉시티가 가능한 아웃컴스 넘버라고 하셨는데, 그럼 그때는 모든 경우의 수가 같은 확률일 때, 균일한 확률을 가질 때만 그걸
네.
그 넘버가 나오는 건가요?
네. 그게 약간 내가 그 스페셜 케이스로서 이야기를 좀 이해를 돕느라고 한 거고요. 네. So so this is our original softmax loss, right? And then it doesn't matter how many classes we have originally. So suppose our problem is the multi-class classification among 1,000 different classes, or maybe 10 different classes, or maybe just 5. Okay. So regardless of the total number of classes, at the end, after training our classifier, and then our average loss of this softmax loss was like PI was 0.5. Okay, so that is the average loss. So what does that mean? So this PI is what? So more exactly, it's like this PYI, right? The predicted probability corresponding to the ground truth one, right? So if given the particular image, and then its ground truth was cat, and then what is the predicted probability that our classifier assigned to the cat class, right? So on average, suppose that probability was 0.5, okay? And then this loss value of negative log 0.5 is possible for each of all the classes, right? So even though we have 1,000 classifier, our loss function, loss value is ending up with this guy, or if we had 10 different classes, our loss may have the same value and 5 classes, and also the loss may be having this value, right? So in this case, roughly, it will be much more difficult to achieve this level of softmax loss given much more number of classes, right? But anyways, if you ended up having this loss value of negative log 0.5, and then it means that your classifier is roughly predicting like picking up one among the two, and among the two, the ground truth answer exists. Okay, so that's the meaning of it. Okay, so your classifier has assigned the probability of 50% to the ground truth probability, and then it doesn't matter how many other or negative classes you have. So in this case, the negative class would have 999 and 9 and 4, right? But it doesn't matter. I mean, all the negative classes and the total amount of probability that your classifier assigned was the rest of the probability of 0.5, right? So it means like this situation is equivalent to picking up like the ground truth values among the two equally possible kind of cases. So does it make sense? So in this case, the perplexity will be 2. And if this value was 0.25, and then what is the probability? I mean, the total probability that the classifier assigned to the all the negative classes, it will be 75%, right? So in this case, it doesn't matter how many negative classes we have, but the total number of probability that our classifier kind of assigned to the negative class is 75, right? 75%. So that's the important part, or that's the all the information that we need to evaluate our classifier's performance, right? And that's how this perplexity measure is computed, or the softmax probability, softmax loss is computed. Okay. So in this case, it's like picking up ground truth among the four different classes. Any questions? 혹시 좀 뭐 이해 안 가면 내가 저기 한글로 다시 설명을 해줄 테니까 이야기를 하세요. 오케이. 오. So it's called the wisdom of crowd. So majority of students gave the wrong answer, and then it means I might be wrong, right? So, actually, what I did was I recognized that the answer was lying in the middle too much, so, like between B or C. So I wanted to have one question has an answer at the extreme value of A or D or E. But anyways, so the correct answer is A. I can almost, there is a case that one-dimensional function can be powerful than, I don't understand this question in the middle. Can anyone elaborate it or explain a little bit more? Okay, maybe then, maybe the student can take, can discuss offline or after the class with me. Both of two models are not independent from. When you say independence, I want to know what kind of aspect you intend to. I think both of two models are not independent from the coefficient of an x. When you say independence, I want to know what kind of, So it seems to be related to kind of this question, right? So in this particular case, if we have a bottleneck layer that has a much smaller number of nodes in the intermediate layers, and then we can always, we are restricted to have the fixed ratio, fixed ratio parameters assigned to x1 and x2, right? So if we just, so in this case, that fixed ratio is like 2 to 3, right? But in this case, we can just freely set up or assign any different parameters of 2 and 3, and maybe 5 and 1. So certainly, Z1 has the different ratio between x1 and x2 as 2 to 3, and Z2 has the ratio of 5 and 1, right? So we basically have a freedom here to choose whatever ratio that we want to obtain each of Z1 and Z2, right? So that's that way this one layer is more powerful, right? Okay. So I hope you guys studied carefully this backprop lecture on the backprop. Okay, so this is really the key concept to train whatever complicated neural nets. Okay, so whether it's just a standard fully connected layers or convolutional neural layers, neural networks or recurrent neural networks or any other types of neural nets, and sometimes. This backpropagation doesn't work. In the case of having some special layers of having some kind of discrete kind of outputs. So in order to understand why a particular layer is not, it's not working with the through the backpropagation. You have to have a deep understanding of this backprop. Okay. Let's see. So I want to give a little bit more intuitive understanding by using a simpler kind of example. Let's just consider this linear regression of having a one-dimensional input of an x, and then our model is ax plus b, and then let's just draw our computational graph. So in this case, so this is one way, like this, and then here we have an a and b, placed at the edge. But when thinking of the backprop, so this is not a good way. Okay, this is not a good way. So all the variables and the parameters, whether they are parameters or the variables. So in this particular case, a and b are parameters that we have to find the optimal parameters, right? Optimal values. And then also x is our input variable, right? But from the perspective of a backpropagation, they are all the same, right? So we shouldn't, backprop doesn't differentiate them in principle, right? So you will see why. And so in this case, I can draw this computational graph as this guy, A. So it is multiplied together, and we have another node B, and then they are added together. So this is Y, right? Okay, then suppose we have just one single training data of x being 1 and y being 4. And then the current parameter values are 2 and 1 for a and b respectively. So in this case, so we typically set up, so I think you have understood some examples shown in the lecture. So x is maybe 1 and 2 and 2 and 1 and 3, something like that, right? And then we set up the gradient value as 1 at the final output node, right? And where does this gradient value of, initial gradient value of 1 come from? So we have to actually compute our, we have to complete our computational graph from the loss function. What is our loss function to minimize? So why do we compute the gradient? It is because we want to minimize some objective function that we want to minimize, right? And so we have to represent our objective function as a computational graph. And so what is our objective function? From using least square or L2 loss, in the linear regression case, our loss function will be this, right? So we have just one single data items. So it's like this, right? And then also, if we have another examples like 2 and maybe 5, and then our loss function can be represented as this, right? Okay, but let's just consider the simple case of having just a single data item, and then let's suppose so this is the predicted value, right? And then this guy is our ground truth value, and then this guy is y and minus, right? So that is up to this point, and then the input value to the input value squared is our loss function, right? So now we completed, or we finished our computational graph to represent this loss function, right? So that way we want to minimize that loss function, right? So starting from here, so from here we apply the chain rule over here as this. So what is the chain rule? First of all, we just think of that function, entire function itself, as the single variable x, right? Single variable x, and our loss function is just this, right? And so in this case, so this is our x. Currently like temporary like capital X, and in this case, what will be the partial derivative or the gradient value with respect to capital X at this point? It will be just 1, right? Because whatever function that we have, and then if we just treat it as just a big X, and then if we compute the gradient, and then it will always produce 1, because y equals x, and then its gradient will always produce 1, right? So our 1, or the gradient value, will start from here as 1. Okay. So in this case, 1, and then y2 is 5, and then it's -2, and then it's 4, right? Okay. So far so good. And then now we have to compute the gradient at this point, right? At this point. And then it is like, so how does chain rule work? Yeah, we obtain the gradient as 1, and then we now get inside of this original capital X, and then yeah, we now set this guy as X, okay? And then in this case, this value will be our temporary capital X, and then X squared, right, will be our L, right? And then in this case, yeah, we just have that value and multiply with 2x, right? 2x. And then what is this 2x? So x was initially -2, and then it's -4, right? And then -4 is actually multiplied with, yeah. So the gradient at this point will be -4 times 1, and so like this, right? And then this value, yeah, we have to backpropagate this node, and then this node, we now have this this guy, and this guy is actually like x minus y is this node, right? And so if we compute the partial derivative with respect to x, and then it will be 1, right? And so 1 is multiplied with this value, right? And then what about this guy? Partial derivative with respect to y, it will be -1. And so this -4 -4 will be multiplied with 4, right? Right? Okay, and then now this -4, in the case of add gate, and then it's x plus y. Here we have an x and y as a temporary capital variable, and in this case, yeah, the partial gradient derivative will be always 1. So that way, this gradient will be just duplicated as the same values, right? And then in the case of this multiplier, the gradients are switched, right? Switched. And so it's like -8, and then it's -4 because this guy. Okay. So this is kind of a mechanical process that we will follow after we compute. After we complete. Yeah, this computational graph that represents fully our loss function, and then we just backpropagate through this computational graph, right? Okay, so here, yeah, this mechanical process, you can just train yourself by following these mechanical process. But what I wanted to emphasize here in this case is that through this backpropagation or completing this computational graph in terms of the forward propagation values and also backpropagation gradient values, it doesn't differentiate whether a particular variable is parameters or input values or intermediate outputs. Okay. So what does that mean? Okay, what does that mean? So usually we just use the parameter that we want to update through our gradient descent is those two values of an a and b, right? So if a was 2, and then yeah, let's use the step size of 0.1, and then times -4, and then 2.4 will be our updated parameter value A. And in the case of B, it was 1. Oops, yeah, it has the same gradient value. Okay, so this will be just a result of one step of gradient descent update, right? So in this case, let me point out this thing. Can we just update x value as well, right? So let's suppose we update x by using the gradient descent as 1.8, right? So ideally we have no problem in doing so, right? So the theory of this backpropagation doesn't prevent you from updating this x value, okay? And then why do we not just update this x value? Okay? It is because it just doesn't make sense, okay? It doesn't make sense, okay? So what's the meaning of updating the input value x, okay? So it's like this. So you have a particular height and weight, for example, like 80 kilograms and also 160 centimeter, which is who is certainly like overweighted. And then this guy has the diabetes as a particular disease, okay? So in this case, your current model is saying this guy is only having the probability, is only 80% of having the probability of having the diabetes, okay? So in this case, the ground truth value is 1, and our prediction value is only 80% of of having diabetes, right? So in that case, we would want to minimize the loss value in order to make it small in terms of the difference between the ground truth value of 1 and the current prediction value of 0.8, right? So in this case, the meaning of updating A and B in this manner, is that we want to just minimize the difference or make the difference smaller or minimize our loss function, right? And then what's the meaning of updating x value? So x will be our feature value, so it will be considered as maybe either height or weight. So I'm currently 100 kilogram and 160 centimeter, but in order to minimize or make the difference between the ground truth value and the predicted value smaller, and then this x value can be updated as this value, and then it means that if we update x in that manner, and then that is just another way of decreasing the loss function value, okay? But suppose that kind of updating is saying that, okay, so I'm currently 100 kilogram and 160 centimeter, but in order to decrease the loss function value, and then my weight of 100 kilometer should be larger as 110 kilogram, okay? So if I increase my weight, and then the current loss value can be smaller, okay? Can become smaller, okay? So that is certainly, one legit way of decreasing the loss value, right? But as I mentioned, that doesn't make sense because we cannot just freely change the input feature values, right? So given a particular person's height and weight, we cannot freely change them, right? So that way, in practice, it doesn't make sense to update these input feature values, okay? So that's why we don't just apply gradient descent on the input feature value of an x, right? Even though we have no problem of obtaining gradient values, whether they are just the parameters or the input feature values, okay? But so you will see, so interestingly, sometimes we are actually updating that input feature value sometimes depending on the task settings. So one representative example is this guy, style transfer. So I think you have seen this kind of example of giving this a realistic photo and another artistic images, and then you kind of impose that style from the artistic images into the given realistic photos, and that way we obtain this output, right? So in this case, what will be our input feature values or input values? Because we want to change, because we are giving this image as an input to our model, our machine learning model, typically, implemented as a deep neural networks, and then height, the input values corresponding to height and weight are the pixel values in this particular case, right? So we want to, optimize or change the input values in this particular task setting. So in this case, it makes sense to change the input values, right, for this particular problem called the style transfer. Okay. So later you will study this example in more detail. But anyways, I wanted to focus. I wanted to emphasize that whether they are parameters or input values, you have no problem of applying gradient descent. Okay, and also there is another type of node in this simple example. So input values and parameters of an A and B, right? And also we have all these intermediate nodes, okay, which are typically corresponding to the nodes in the hidden layers, okay. So those nodes, those internal or intermediate nodes will also have these gradient values, right? Okay, and then can we just apply the gradient descent on these intermediate nodes? For example, like given this value, so something like this, 2.4, right? So we have, in principle, we have no problem of updating that intermediate values through the gradient descent, right? So that way we can directly optimize or update the intermediate values. But in this particular case, it doesn't make sense either, okay? Why does it not make sense? Because this intermediate node is not an independent variable, right? It is actually like output from another, other independent variable. So in this case, X and A are kind of independent, can be viewed as an independent variable that we can kind of change their values, right? But those intermediate node is actually the output from those independent nodes, right? So that way, it doesn't make sense to directly update this intermediate node, okay? But still, that kind of thing of directly updating intermediate node is also possible, and some advanced method is actually using it, okay? So although there is no representative case that I can describe easily, but in principle you have, I want you to understand, in principle that is also possible, okay? And if needed, you can utilize that kind of idea, okay? In that case, it's like intercepting some intermediate values into some other values that can directly optimize or minimize the loss functions, okay? But anyways, okay, and then and I want to discuss a little details about why chain rule works. Why chain rule works. Okay, so for example, like this. So it is actually a composite function. Composite function means x is first going through this sine function, and then this output, intermediate output, is also going through the squared function, right? So that is the simple computational graph of this guy. Okay? Okay, and then in this case, let's see, it is c and z, and y is sine x, so this is y and z. Okay. So we want to obtain the partial derivative with respect to x, and then it can be written simply as this form, right? And also it's like it is actually even be written as this guy, right? So suppose this guy is the function that we want to minimize, okay? Mean of z, or we want to minimize sine x squared, okay? So in this case, currently x is maybe 30 degree or something, okay? Or (30도가) 몇 파이죠? Okay. 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 So in this case, we want to obtain the partial derivative or gradient with respect to x, right? So in this case, it is like this. So we start from here, gradient of this. So it's like pi over 6, and then it is 1 over 2, and it is 1 over 4. So that is a forward pass, right? And then the backward pass will be 1. And what is this guy? So it's like, so we just look at this sine x as capital X temporarily, and x squared, and 2x, and then x is this value, and then this value is 1, right? And then it is actually 1 times 1. So it is 1, and this is also 1, right? And then what about this guy? So when x is pi over 6, and then it is having this, I mean this is a derivative, so right, so this is the backprop result, right? Okay, so why should we multiply all these values? Why should we multiply all these values? Why should we multiply this? So it is, yeah, so yeah, let me just explain it in maybe 2 minutes. So how this chain rule works, or the intuitive understanding about this chain rule, is as follows. So we want to have, we want to obtain how much changes z has with respect to the changes of an x, right? So it's like this. So if we have this kind of function, and then what will be the derivative at this point? It would be the slope of this. And then what's the meaning of it? The meaning of it is, so if we just move like with the 1 centimeter larger, and then how much y value changes, right? So that ratio is the slope, and that is the definition of the gradient, or the first order derivative, right? And then what about the chain rule? Okay, so this is like x to y and y to z. So we want to obtain how much z changes with respect to the changes of an x, okay, when they change with the 1 centimeter. So this is an x. So this is an x, right? And then suppose when x changed with the 1 centimeter, and then y changed with the like square root 3 over 2, right? So that is the changes, the amount of change of y, okay? And then when this amount of change occurred for y, okay? So it's like x and y and z, and so this corresponding y value was 3, and then we go to the value of 3 at y, and then here we consider this slope at this point, right? So this is still, I mean, dz over dy is actually the amount of changes of z when y changes just 1 centimeter, right? So that's the meaning of this guy, or the slope of the graph between z and y, right? But y does not change only 1 centimeter, because that is just a dependent or intermediate variable obtained by x. So when x changes with the 1 centimeter, and then y change it with this amount, and then we have to replace this value as like square root 3 over 2, right? So that way we have to multiply this changes when y changes the 1 centimeter by the amount of this value, okay? So that's the meaning of just keep multiplying, yeah, those slope values. Okay. And then what is this guy? The first one is always like this graph. So z equals z. So in this case, whatever positions, the slope will always be 1. So it will be just 1. Okay. I'm not sure if it's yeah, it helped your understanding about why this chain rule should be true, but yeah. Okay, so that's it for today. And then until Wednesday, I will assign you guys to for some other additional video lectures to watch, and then that will be also the scope of the quiz next class. Okay, thank you.